Good morning, everyone. Thank you for attending. It's a great pleasure to welcome today's speaker, Dr. Kirstin or Kiki Schulz. Kiki is a research fellow in the Cryos group at the Oden Institute and working with Anne Nguyen, who's also here, Helen Piller, and myself. So before joining UT Austin, Kiki was a postdoc at the Alfred Wegener Institute for Polar and Marine Research in Bremerhaven, and also at the Royal Netherlands Institute for Sea Research. A number of projects that she was involved with. Recently, the Mosaic expedition, this drift in the Arctic. She was also involved in the effort called Peanuts, which is the primary productivity driven by escalating Arctic nutrient fluxes. And before that, on the role of sediment for salt marshes, and so where she worked on mud. Kiki obtained her PhD in physical oceanography from the Institute for Baltic Sea Research in Warnemünde, and she has a master's in applied mathematics from the Technical University in Clausthaus-Tellerfeld. Kiki's recent work is on mixing processes in water mass transformation in the Arctic, and also on turbulent exchange processes and ice-ocean interfaces. And in this capacity, she's actually involved in an NSF axle net on Greenland ice sheet ocean interactions. That's led out of Scripps and with the UTPI Anne Nguyen. And so today's talk will be on changing mixing in the Arctic Ocean. We look forward to your talk.
Yeah, thank you very much. Does this work? Good. Yeah, I'm talking about mixing in a changing Arctic Ocean. And this is polar bears from the Mosaic expedition, which is always a nice first slide. This is some of the people I've worked with in this effort, just to illustrate that science and especially Arctic research is a team effort because it requires a lot of manpower and wouldn't have been possible without numerous co-authors, collaborators, people helping with the data, also the technicians, the people on the ship, the crew. They're all very important. This is the Arctic Ocean, below the sea ice, the topography. And so we're having a deep basin here in the middle. It's around like 4 to 5 kilometers deep. There's a ridge in the middle, the Lomonosov Ridge, that separates the Western and the Eastern Arctic Ocean. Here we have the big connection between the Atlantic and the Arctic Ocean, the Fram Strait. And then the shelf seas here, very wide shelves, the Barents Sea, Kara Sea, Laptev Sea, and so on. We know that now, even though the topography could be a little bit more improved, but we haven't known that for a long time because the Arctic is very inaccessible with all the ice cover. And until the 19th century, it was absolutely unclear if the Arctic actually is an ocean or if it's land. If it's an ocean, is it an ice-covered ocean or not? Is it like a deep ocean or like a shelf sea with a lot of islands in there? And there was a famous German oceanographer and general scientist, August Petermann, and he had the very valid hypothesis at that time that the Arctic was an ocean, yes, but definitely not ice-covered. And there were a lot of people who were along these lines. And the argument there was that with all the hot water from the Atlantic that is flowing into the Arctic Ocean, it's not possible that ice can stay there just because of the amount of heat that is transported up north. And that the ice is merely around the rims of the continents where the fresh water from the rivers runs in, that can freeze over, but the center of the Arctic, definitely not ice. Fridtjof Nansen was one of the godfathers of polar oceanography and of oceanography in general. And he finally confirmed what's going on up in the north during his Fram expedition. That was him and some people and sledge dogs getting frozen into the Arctic Ocean in front of the Siberian coast on this wooden vessel that's called Fram. That's where the Fram Strait got its name from, because they drifted with the transpolar drift. So the general circulation or transport pattern that pushes ice from the Siberian coast towards the Fram Strait, frozen into the ice with this ship for 3 years, well, and did science in the Arctic Ocean. And they found out that once and for all, the Arctic really is an ocean, and it's a deep ocean. Actually, how deep it is, they couldn't perfectly determine because they didn't bring enough ropes, because they suspected it to be a shallow ocean. And well, it was deeper than all their rope lengths combined. He confirmed the transpolar drift by basically riding on it. And he also noted the Coriolis effect on the ice drift. That was something that was further elaborated by his disciple Ekman. And what he also found which will be a topic of this talk, is a temperature anomaly at greater depth of the Arctic Ocean. So the surface layer was very, very cold, close to freezing, but at a couple of 100 meters depth, the water was actually plus 2 degrees Celsius, so it was warmer than the surface water. And that was kind of surprising, and we will talk about that later on. Another fun fact, he abandoned ship at some point to try to reach the North Pole on skis, failed, had to overwinter in Franz Josef Land, but that illustrates how important like politics and media outreach already was 125 years ago, was the North Pole. And nowadays we have a lot of great expeditions going on. I had a couple of big expeditions going on in the Arctic. In the Beaufort Gyre, we had Chiba, then we had N-Ice from the Norwegians, and recently, 2 years ago, Mosaic, where I was participating on the German research icebreaker Polarstern, and that was a year-long expedition, basically recreating what Fram did, what Fridtjof Nansen did 125 years ago, starting here in front of the Siberian coast, a little bit further further into the Arctic Ocean because the ice edge was further north. And then we got locked onto a floe in October and then drifted with a transpolar drift across the Arctic. Here we went a little bit faster than anticipated. Here we had to take a little break because of COVID. We couldn't get supply icebreakers anymore to exchange personnel and equipment. So Polarstern had to come out of the ice, pick people and equipment up in Spitzbergen, including me, and then go back to the ice. And then we continued the drift at the same flow until the flow broke. And then with the last leg of the expedition via the North Pole this time, we went up north and the drift continued here. And we basically brought all the equipment that is modern oceanographic equipment, plus atmospheric research, ice research, biogeochemistry, ecosystem. So the flow was packed with instrumentation. We had a distributed network. We had remote campaigns supporting that. So basically we tried to measure everything. So, and what we know about the Arctic Ocean and the circulation patterns in there is, here's the map again, the shelves and the Fram Strait here, that the Atlantic water flows into the Arctic Ocean. And in the Fram Strait, north of Heimbach Plateau here, and in the Barents Sea, it's still very high up on the surface. So the heat that comes with the Atlantic water reaches the surface, can melt the ice. That's a reason why the Barents Sea here is often ice-free, even in winter. That has always been the case. And then, because of Earth rotation effects, it propagates along the rim of the continental slope in the Arctic. And because it loses a lot of heat to the surface in this region, it like successively dives deeper until it's like a couple of 100 meters deep. And then it's effectively isolated from the surface layer and all the ice. So August Petermann, the guy who said like the Arctic Ocean is ice-free, he was kind of right, because the Atlantic water brings enough heat into the Arctic to melt all the sea ice, but it stays at depth, so it can't reach the sea ice. And this is how the vertical structure looks like in the sketch. In the Arctic, this is like the Laptev Sea region maybe, and we have on top, well, ice. And below that, we have a cold and relatively fresh surface layer. It's fresh because there's a lot of river runoff coming from Siberia and freshening the surface of the ocean. And when sea ice is formed and salt water freezes, the ice that is formed is actually pretty fresh. And the salt that was in the seawater gets rejected in a brine that sinks down, gets mixed a little bit, and then sandwiches in to a layer below the surface layer that we call the Arctic halocline. Halocline is a vertical layer with a strong stratification with a strong density gradient because of the salinity. So the water here is very fresh, the water here is very salty, and that's what we call a halocline because salinity is increasing. And this halocline is like a barrier between the surface layer and this very warm but very salty Atlantic water underneath. So this is really what shelters the surface layer from the heat. And how do we measure that? This is one of the backbone instruments for physical oceanography. That's a CTD. CTD stands for conductivity, temperature, and depth. And it measures conductivity, temperature, and pressure, from which you can calculate depth. And from conductivity, we get salinity of the ocean. And this specific CTD has a ton of other sensors on it, and these rosette, where you can get actual water samples from different depths. And a typical profile of temperature and salinity in the Arctic. that we can measure looks like this. So we have here the relatively fresh and very cold, close to freezing surface layer. Then we have this increase in salinity below. And here you can see this bump in temperature with relatively warm, 2.5 degrees Celsius, Atlantic water that is found at depth. And when we compare that to the sketch, that lines up pretty well. Right. Another one of my favorite instruments to measure the ocean is a microstructure turbulence profiler. There's like this height, 1.20 m maybe, thing, with a sensor packet down here, and that's lowered into the water on this orange cable. And while we can't, and it has little shear sensors on the tip, and these shear sensors can measure turbulence. So the very small scale, centimeter scale, overturns in the water. So when you steer it really hard, you have a lot of turbulence. When the water is very quiet, you don't have a lot of turbulence. And this is what this instrument can measure. And these sensors we can't put on the big CTD because that's a heavy thing that is lowered at a high speed through the water column, and it creates its own turbulence. This instrument that falls really, really slowly at 0.5 meter per second through the water column, very undisturbed with a lot of cable. So there's never like any pull on the cable, always slack. And because it falls so undisturbed, it can beautifully measure turbulence. And this is how 2 example turbulence profiles look like. And for a little visualization for turbulence, because I'm going to use that word a lot, this is a flow with dye that goes from left to right over this grid. You can see here the flow is very laminar. That would be like the gray profile approximately. And here, after it hits the grid, the flow is disturbed. The laminar kinetic energy is getting transferred to like mixing turbulence. And this is the black profile, more or less. So when I say turbulent, I mean thing with the little wibbles and whirls. And not turbulent is this part. All right. Some more basics of oceanography. We've seen already that the ocean has not uniform properties in the vertical. The water is not all the same. In fact, the ocean is density stratified like a cocktail, with like the light liquids, like the alcohol being on top, and the dense liquids, like the syrup and the liquors, being at the bottom. And in contrast to a cocktail in the ocean, it's the salinity and the temperature that determine the density of the water. So in general, warm water is lighter than cold water, and fresh water is lighter than saline water. That's a nonlinear relationship. Sometimes, as we've seen in the Arctic Ocean, it gets canceled out, and you can have warm water that is dense because it's very saline, which compensates for the make it lighter effect of the temperature. And in general, the light water is on top, the dense water is at the bottom. But in reality, it's not a linear profile very easily. But there's a lot of structure in the density profile in the ocean because we have the advection of water masses, so currents that just push water masses horizontally around the ocean. And that makes that the water column is sometimes like heavily stratified with large density gradients, especially at like the interface between 2 water masses, and sometimes weakly stratified, so not a big density gradient, more homogeneous conditions. So that's what advection does. And then we also have turbulence that destroys stratification. So when you have something like a soup or so that has like a lot of gradients in there and you steer really hard, the gradients go away. And this is what typically happens in the surface and the bottom layer. So at the surface, you have winds and waves that steer the ocean. So you have the surface mixed layer where temperature and salinity and density are homogeneous. And the same happens at the bottom because there the currents experience bottom friction and the laminar flow gets translated into turbulence, gets translated into mixing, makes a mixed bottom layer. There's also a lot of mixing mechanisms in the interior, but it's like the science for itself. But then again, it's not only that turbulent mixing destroys stratification, it's also that stratification suppresses turbulent mixing. Because when you try to mix something that is heavily stratified, you have to work against the stratification. Bringing something dense up to where it's light is much harder than just like steering something that is already well mixed. So, and this is, for example, what happens in the Arctic halocline, where we have this strong salinity stratification and mixing in the Arctic halocline. We will see that later, really is low because it has to work against all the stratification and just can't overcome. Right, and to illustrate a little bit how dramatic the effect of turbulence on ocean stratification can be, we go back to these two profiles that I showed from the microstructure profiler, the gray one very low turbulent, the black one very high turbulent. And I show you the corresponding temperature profiles. And they are from the same region, same water depth. They should look the same, but they don't. The only difference is turbulence. And what this turbulence did was, in the undisturbed, non-turbulent station, we had this warm surface layer. It was summer, no sea ice, so it was warm. And then here is the cold Haloc line, and here is the warm Atlantic water blob. And when you steer it well enough, this Atlantic water layer is completely eroded. You warm up the Haloc line, you really bring warm water into the Haloc line, and you even have exchange with the surface mixed layer, which is really hard because there's a huge density stratification between the surface mixed layer and the ocean below. So you need a lot of turbulence to overcome that, but it can happen. All right, so now, why do we care about mixing in the Arctic Ocean and what's the future of the Arctic Ocean? This is me, by the way, this is Michael on Mosaic during a midterm party. Mixing in the Arctic Ocean and why should we care? And now I have to make clear, I'm talking about like the Laptev Sea, Siberian Sea parts. The situation in the Western Arctic Ocean and also in this Fram Strait area is slightly different. But in general, in the Siberian sector of the Arctic Ocean, it looks like this. We have the ice cover on top and the warm Atlantic water that also is the largest nutrient source for the Central Arctic, deep at the bottom, separated by the Haloc line in between. And the Arctic Ocean is not only light limited because of the sea ice and the short light season, but it's also extremely nutrient limited. So all the algae that live there have really a tough time because they don't have enough food, they don't have enough light, and they have a very, very low level of primary productivity. So there's not a lot of algae growing that is the basis for the whole food web. And this led to the Arctic being a very, very specifically adapted ecosystem that is unique to this planet. So a lot of species that live in the Arctic are there because it's such a hostile environment. They had to adapt a lot, and it's an endemic ecosystem. And part of why this ecosystem is so special is because of the nutrient limitation. And this is because vertical mixing in the Arctic with this strong Haloc line in there is just too weak to bring this large reservoir of nutrients that we're having down in the Atlantic water up to the surface. But now, with climate change, the ice cover is receding. And the ice cover is one of the reasons why turbulent mixing in the Arctic Ocean is so low, because it hinders the energy transfer from the atmosphere to the ocean, because it's like a sheet in between. And without ice, it's much easier to transfer energy to the ocean by winds, but also by like displacing the water body and letting it move around, which is ultimately energy that can be translated into turbulent mixing. Right, and with this increased mixing regionally, we have increased nutrient and heat transport to the surface. And the heat transport melts even more sea ice. That's a little vicious cycle. But it also amplifies the availability of nutrients in the surface layer where the little algae grow. And that leads to more primary productivity. And when there's more primary productivity and less sea ice, the conditions become more friendly for species that normally live in the Northern Atlantic. So these species migrate into the Arctic Ocean, and once conditions are friendly enough for them to survive, they absolutely outcompete the Arctic species because they're bigger, they're fitter, whatever. And the only advantage the Arctic species have is this high adaptation to the system. But if the system becomes like more broadly friendly to any species, it actually might disappear and get replaced by North Atlantic species, which would be really sad because, well, a very unique ecosystem. Right. So this is why we care about mixing in the Arctic Ocean. And this was all introduction. And now we're coming to the research I did during my time at the Alfred Wegener Institute, and also continue a bit with that nowadays. And the first data I'm showing is from the Mosaic expedition that was Polarstern locked in the sea ice in Arctic spring. And from Mosaic, we have a 1-year time series of vertical profiles of turbulence in the Arctic Ocean, which is pretty unique. I mean, that's 1,685 profiles that I personally all quality controlled, which was quite some work. So and in the top panel, we have the turbulent dissipation rate, which is a measure of turbulence. So red is very turbulent. Here's the vertical axis, and this is like the year of mosaic. And in the lower panel, we have a measure for the stratification. So stratification means like the huge vertical density gradients that suppress the turbulent mixing. And blue colors are strong stratification, white colors are no stratification. And you can see here, this is the Arctic halocline. Here again. Here in March, April, it disappeared because the surface layer in this region and in that season was very saline. So you had no salinity gradient anymore because the surface layer already was same salinity as the lower ocean. And you can beautifully see how stratification bounds turbulent mixing. So this turbulence is coming from the surface, friction under the sea ice. But as soon as it reaches the halocline, it disappears because it can't penetrate further, because it's really like a sheet in the ocean that hinders vertical mixing and transport. And when the halocline disappears here, it trickles down a little bit deeper. But this is the really, really low levels of turbulent mixing. This was the break where we had to be picked up in Spitzbergen, and this is the break where the relocation to the flow further north happened. Right. So in conclusion, in the central Arctic Ocean, strong turbulent mixing is very much confined to the surface layer, bound by the halocline. It's slightly increased when the halocline disappears. And also here, where we were in a region with very complicated topography. But overall, it's really, really low levels of vertical mixing. And as a number example, we have in the winter Arctic halocline turbulent diffusivities. So yeah, turbulent diffusivities. This is like the coefficient to mix in the vertical on the order of 10 to the -6. And the estimated global average in the oceans to close budgets that we need is 10 to the -4. So this is 2 orders of magnitude. So basically nothing gets transported over this Arctic halocline in winter. It's like a shield layer, right? So it's a little bit boring. What is way more interesting is turbulent mixing above the slopes of the Arctic. And when I showed these little sketches before, and I talked about increased vertical mixing regionally, I made the vertical mixing signs on the slopes of the basin, and that was deliberately because slope mixing is the thing that is really interesting. So, and this is data from a cruise in summer 2018 to the Laptev Sea in front of Siberia. And there we, on 100 stations, saw this classical profile of low turbulence in the mid-water column, then turbulence in the bottom layer, and turbulence in the surface layer, which is still what we expected. And this is how like 100 profiles from that cruise looked like. And that has implications for the transport of whatever tracers. For example, here we have a station on the shelf at like 100 meters depth. And turbidity, that's a measure for how much dirt, sediment lifted off the seafloor is in the water. And we can see here in the bottom layer, the turbidity, so like the amount of particles in the water that is kept in suspension, is increased, but only where it's turbulent. So as soon as the turbulence decays here, you also can't mix the sediments further up. So on the shelf, we have this bottom layer of relatively turbid waters, dirt kept in suspension that wobbles around a bit, doesn't really go anywhere, but it's kept in suspension, it's mobile. And on the other side, in the surface layer, what we can see here is that nitrate, as a measure for nutrients in general, is very much depleted in the surface layer. That's already late in the productive season, so in end of August, beginning of September. And the algae have used up all the nutrients that were available in the surface layer. There is a lot of nutrients still available at depth in the Atlantic water layer, but turbulent mixing is just too weak to transport it upwards, and that hinders primary productivity. So algae can't grow anymore. Right, and then we had this profile. So turbulence increased over 2 orders of magnitude throughout the whole 350 meter water column. And this was a very, very exceptional station. And what we all thought was sensor malfunction, but it's not. So this is real turbulence that we measured there. And I've shown you these profiles before. That was the gray one and the black one. Now it's the red one and the black one. And that mixed the water column like tremendously. This is temperature. The Atlantic water layer is gone. The halocline got warmed, exchanged with the surface layer. This is the nitrate, so the nutrient concentration. at a reference station that is close by, depleted in the surface, big reservoir here. And then when you mix it enough, you bring all the nutrients from the deep layers up to the surface. And the decrease here is in parts due to uptake of the nutrients by algae already. So the algae there started growing again. They started consuming these nutrients. So this is why we have the gradient at the surface. Right, and this was exceptional. So that's really something you want to see when you go on these expeditions. And the questions we are asking now, where does this turbulence come from? Why is it turbulent there? How often does that happen? Is that a once in a lifetime thing, or does it happen regularly? And does it have a notable effect on transport in a pan-Arctic sense? Or is it just like, well, yeah, it happened here once, but in the global picture, it doesn't make any difference. And that's the questions I'm gonna answer in the next 10 minutes. Right, how was the mixing generated? For maybe a bit better orientation, this is again the map of the Arctic Ocean. Here's Fram Strait. And where the red dot is, this is where we measured the transect. So going from shelf to the deep ocean and have stations on the way where it gets deeper along the continental slope. And these are 5 profiles we measured on this transect. This is on the shelf. This is turbulence again. On the shelf, we have the turbulent bottom layer and the turbulent surface layer. Again, this is our very, very turbulent station at around 350-meter depth. And here in the deeper basin, turbulence is again back to like background levels, not very turbulent. And we were extremely lucky that this turbulent station happened to be close by an instrument mooring that we had here. So here at the seafloor for 3 years, there was an ADCP standing. ADCP is an acoustic Doppler current profiler that basically sends out an acoustic signal that gets reflected by particles in the water. And then by the Doppler effect and maybe a little bit of magic, it can determine how fast the water is flowing at different depths. And right at the bottom here, there was another CTD mod that recorded temperature and salinity from which we can calculate density. And these are the data records prior to when we measured the very turbulent station that was happening here. The increments are 1 day. And here you can see the current velocity, depth averaged. Black is in the direction that goes parallel to the slope, so along the slope. And gray line is in the direction perpendicular to the slope, so up and down. And what we can see here in the gray shading is right prior to the measurement of this turbulent station and like 2 days before, there was a current surge coming by. So an absolute anomaly in the current. We just had in this normally very quiet region where the water is not moving too much, you just had a surge rushing through for a day. And this current surge in the along slope direction also had a component that was directed offshore, so in the downslope direction. And what happens when you push water offshore above a very steep slope, you also displace it vertically. So you push the water away and then shallow light water from shallower positions gets pushed down the slope. And this is what we can see here in the density record. So while the flow was directed off slope, there was a drop in density. So water from shallower areas arrived at the mooring. And this drop in density, that corresponds to like a vertical range of around 100 meters at a 350-meter water column. So that was massive, like how much water was transported offshore. And these current surges, they are what we call continental shelf waves. And they are generated by atmospheric forcing, pushing water towards the coast, having coastal convergence, and an inclined sea level. So the sea level at the coast is higher than the sea level at the center, via the Ekman transport, and the wind forcing keeps it in position. But when the wind forcing decays, this inclined surface is unstable, of course, and the water whooshes back. And with earth rotation effects, it gets this kick in the along slope direction, and this forms a continental shelf wave that goes around the Arctic Ocean. And for some reason, we don't really know why, maybe it was topographically steered, or it's still a reminder from this backwards whooshing, it had this off-slope component at this position. Right, okay, that was a lot. I say it again to recap. What happened prior to the mixing? So we had a storm event that we observed that was blowing along the coast. Via Ekman transport, it piled up water at the coast, had this angle in the sea level. When the forcing declined, sea surface went back to where it should be, exaggerating this continental shelf wave that propagates around the Arctic and is visible as this barotropic anomaly in the currents, so this current surge that we observed in the ADCP data. And because of the downslope flow component it had, it displaced isopugnals, so it pushed light water down the slope that we observed here. And that resulted in the creation of a trapped lee wave. Because what happens when you push light water down where it doesn't belong, you excite an internal wave at the interfaces of density in the ocean. It's like surface waves, but just between two density layers in the ocean. And these internal waves are a bit tricky to describe, but one characteristic they're having is if they can propagate away freely or if they cannot, depends on their frequency and at the latitude, on the latitude that they are. And the further north you go, the shorter the period of internal waves that can propagate away is. And so up high in the Arctic, there's few forcing frequencies that generate internal waves that can radiate away. And it's certainly not this diurnal or like 1-2 day forcing that we experience. So with this long forcing period, the internal wave that was generated couldn't radiate away, just stayed here, was a trapped lee wave, and then dissipated into turbulent mixing. Right. How often does that happen? So this mooring that was, with the turbulence profile, we were only there for one cruise, but the mooring was in the water for 3 years. So what I did is I counted how many events there were with the current surge going through and this depression of isopugnals. And well, each of the stars is one of these events. And I plotted that against the sea ice extent in the Laptev Sea. So here the Laptev Sea is fully sea ice covered. This is the year, January to December. And here in September, you have the sea ice minimum. And that's 3 different years. And each star is one of these potential mixing events that we observed in the data record. Right, and the lame answer is on average 8 times per year. But the better answer is typically in the sea ice free or less sea ice covered condition, which makes a lot of sense because the energy for this mixing ultimately comes from the atmosphere. And if there's not a solid sea ice cover, it's much easier for wind to move water, right? That also means that if the sea ice, the ice-free season elongates and there's overall less sea ice in the Arctic, these events might become more likely in the future. And now the most interesting question. What about transport? Does these mixing events make a lot of transport vertically in the Arctic? And first we look at suspended sediment. So I told you already about the dirt that is on the continental shelf that is wobbling around in the bottom layer. And this is the same transect I showed you before with the turbulence here. This is our very turbulent station. And in the top panel, you see the particulate matter concentration. So how much milligram per liter dirt are in the water. And you can see here on the shelf, you have the turbid sediment blown bottom layer. And in the deep basin, you have basically just a background concentration, so no sediments. What is known in the Arctic Ocean is that the sedimentation flux at the deep basin, so anything that arrives at the seafloor in the deep basin is mainly transported laterally at intermediate depth from the shelves at intermediate depth to the deep basin, and then it like rains out there. But the process that makes this lateral transport, that was absolutely unknown. Like, why is it transported? This is a possible mechanism to do that, because at this very turbulent station that we had, we also observed a cloud of suspended sediment at intermediate depth, so somewhere between like 100 and 300 meters. And this is like 0.5 kilogram per square meter sediment kept in suspension. And what will happen after the turbulence decays is that this turbid, homogenized layer of water will collapse, spread out laterally, and then the sediments will rain out when the turbulence has decayed and can't keep it in suspension anymore. So this is one potential mechanism that connects the shelf and the deep basin. And why is that important? Because the sediments on the shelf, They are very mobile. They are still in the system. They can be recycled, and they are super rich in organic carbon. So it's mostly dead algae that sank to the seafloor at some point, and they're like loaded with carbon. Once that's at the deep basin floor, it's removed from the system on climate timescales. So this is a pretty effective mechanism for carbon sequestration that removes carbon from the like active cycle of the world and forms oil or whatever in the very end then. Right, nutrient transport. We saw that already. This is the, this is the very turbulent profile. This is a reference station. And this is how the nitrate concentration in the vertical changed and the resupply of nitrate to the surface layer. And from these two quantities, we can calculate a nitrate flux. So how much nitrate is transported vertically. And we can compare the nitrate flux at this station, which is here, with all the other nitrate fluxes we measured at different years on different transects at different positions in that piece of the Arctic Ocean. And this scale is logarithmic. And this is like the average flux here, 0.01 something. And the flux at this very turbulent station was more than an order of magnitude higher than at all the other stations. And if we do a little back of the envelope calculation, is that the flux from these turbulent events 8 times per year over like a 10-kilometer strip of the cross-shelf transect contributes to the overall Arctic average nutrient supply in the vertical, approximately as much as all the low turbulent fluxes over the rest of the area combined. It's like this could be half the vertical transport of nutrients in the Western Arctic. Right. And what we also measured was locally enhanced primary productivity. So nutrient supply is not the same as algae growth. You also have to give the algae time to growth and to utilize the nutrients. But we had biologists with us, and they actually measured primary productivity, and they found it at this position where the nutrients were resupplied to the surface, greatly enhanced compared to the other stations. All right. So in summary, what we found during my project time at AVI, that was the Peanuts project, by the way, that Patrick told us. We found a new energy conversion mechanism for vertical mixing above Arctic continental slopes. And this is something really unique because mixing in the Arctic Ocean is overall really low. And a lot of these energy conversion mechanisms that we have at temperate latitudes don't work in the Arctic because it's so high up that the internal waves that make a lot of the mixing in the middle water column, they can't propagate around there. So this energy mechanism is something really remarkable. And we were extremely lucky to measure that 8 times a year. And it was there while we were there. We also have a first observation of this intermediate nepheloid layer, intermediate dirt layer, above the slopes that far north. And that provides an explanation why lateral transport at intermediate depth in the Arctic Ocean happens, basically. And this mixing event is also potentially extremely important for the resupply of nutrients to the surface layer and might supply the amount of nutrients equal to the basin-wide weak mixing in summer that happens like all the time. All right, I'm done. Thank you for your attention, and I bet you have a lot of questions.
Thank you very much, Kiki, for a really illuminating presentation. Yeah, so I'll open the floor for questions. Be shy. Oh, yeah, question.
Okay. Okay, is this on? Do these events play any role in the mechanical breakup of the sea ice? Is there a correlation there?
Yeah, so this is a summer event mostly. And during that time, there's not a lot of sea ice in the Laptev Sea. What we have seen is that there was exchange with the surface layer. And what you typically can think of is the temperature the surface layer has before sea ice is formed. That is a factor because you have to cool down the surface layer to freezing point before you can start forming sea ice. So vertical mixing in summer has no direct effect on sea ice formation, but more an indirect effect by preconditioning the surface layer to set the stage for sea ice formation. Now the surface layer was really warm in summer, and we actually, like, it was cooled down by this mixing event. So what effect it has on sea ice, tricky to say.
Thanks.
And I should also encourage people online to either raise their hand or chat. Is there someone? Okay.
You really enjoyed your talk. This is kind of a follow-up just about the hysteresis of these areas where you have a lot of turbulence. What's the timescale over which that might go back to being stratified? So like, is 8 events per year sort of keeping that water column mostly unstratified throughout the year, or does it resume quickly?
Yeah, that's a great question. So re-stratification after one of these mixing events happens pretty rapidly. So within a day or two, because it happens over a very small spatial scale. So something like in the order of 10 kilometers in the horizontal where you mix the water column, and it just can't exist there very long because it's a homogeneous parcel of water surrounded by a stratified ocean. So what will happen, we call that gravitational collapse. So it's basically re-stratifying from the outside, and this layer just gets flat and sandwiches in at like its preferred density level. So it doesn't persist for very long. It's like 1-2 days max before it's re-stratified. Thank you.
Thank you.
Thanks for the nice talk. I was wondering, for when you have a lot of sediments in the water column, do those kind of behave passively within the turbulence, or can they back react and affect the characteristics of the turbulence itself?
That's a really great question. It's hard to tell, of course, because we don't have direct comparison measurements. From my experience, and this is more feeling than something, the levels of sediment that we observed there are not enough to have an effect on turbulence. What happens in estuaries, on the other hand, where you have like really massively, it's called liquid mud rather than suspended sediment, where you have super much fine particles being in the water column, or well, suspended or not, they actually have an effect on the density and the stratification of the water because it's so much sediment in the water, and that has an effect on turbulence. But with the concentration we observed here, that's nothing compared to, you wouldn't see it in a water sample. So if you take a water sample, look at it, you wouldn't directly see the turbulence. You really have to filter it. So this is still low concentrations. So the effect they have on stratification and turbulence is rather third order.
Thank you for your talk. So in the Antarctic Peninsula, there is a temperature degree increase about 3 degrees since 1951. You would expect to have the same mechanism, the governing mechanism, or enhance, or there any evidence of that?
So what happens in that part of the Arctic Ocean? In the Fram Strait, so at the very entrance of the Arctic Ocean, where it's connected to the Atlantic water, there are trends in the transport visible, but it's hard to like take these trends apart with like the decadal and interannual variability of the properties of the Atlantic water, because it has like an intrinsic variability, and disentangling trends from long-term variability, that's tough to say, and that's also not my area of expertise. What happens in the Laptev Sea region is something that we call Atlantification, and we don't really see an increase of the maximum Atlantic water temperature, but we see that this Atlantic water layer is higher up in the water column, and that the Haloc line that separates the Atlantic water from the surface is getting thinner and thinner. This is something we have observed, and this is attributed to just a general shift of conditions that are very typically for the North Atlantic, for the Barents Sea still, where the Atlantic water is very high, that these conditions shift further and further into the Arctic Ocean. And in the Laptev Sea, we see first indications that the Haloc line is thinning more than its variability is, but it's very small and very sparse data, so it's tough to see, but this is what we anticipate, and this is what first indications are visible for. Yeah, thank you.
Hi, great talk. Thank you so much. This might be a stupid question, but with the turbulent temperature graphs that you were showing us, I would assume that like very turbulent water would be warmer because of the bottom Atlantic water. And I was wondering, why is it like -1 degree Celsius versus like the non-turbulent is like a little bit warmer? Does that make sense?
You're referring to the Haloc line that was warmed in the.
Yeah, so like the graphs where it's like
Yeah.
it shows the turbulent water having like just like that straight vertical stratification. I'm wondering why that's like really cold and not like really warm.
That's a great question and not at all stupid. So yeah, if you think about mixing like a lot of warm water upwards, it should get warmer, and it did get a little bit warmer. And what turbulence basically does, it mixes all the water. So if you have warm water and very cold water, you end up with like intermediately warm water. And it's not only happening in the vertical, it's also happening in the horizontal. So vertical mixing is in general weaker than horizontal mixing. When I show enhanced turbulent mixing in the vertical, it also mixes to some extent in the horizontal. So you basically take like a cube of water that you homogenize, and the resulting temperature of the water that is then homogeneous in this whole turbulent patch, that is just the result of the end members that you mix together. And it's really tough to say once it's all steered what the end members are, because you just have this one data point, one temperature, one salinity, and then how much of which water has ended up in there, that's really tough to say. But it's somewhere between halocline and warm Atlantic water. Thank you.
Have you thought about the fact that the turbidity and the turbulence are linked? These look like turbidity currents. You know, these look like sediment collapses from the shelf to the slope. Got some big river input, got big sediment prisons. I don't know if you've ever seen geophysical profiles from the Laptev Sea, but there's a lot of sediment there, soft sediment.
Yeah.
It's going to periodically collapse. The events look like they're more prominent when the sea ice is not there. I'm not sure what that correlation is, but this could all be geological.
Could be, I thought of that, but then it would be at the bottom, right? And not in the.
Well, I mean, a turbidity current would be all through the water column.
Yes.
I mean, you know, a big one.
Yeah,
So,
but the sediment concentration wouldn't necessarily decrease again towards the bottom, right?
good.
Good.
Yeah, good. So I don't know, you may have had geologists out with you on the ship. So you didn't say anything about geology, but geology,
We
you
didn't
start talking about dirt, we call it
ocean.
sediment.
Hmm?
I like it being called dirt, though. It's good. It is an interesting thing to think about.
It definitely is. Yeah,
Okay.
and I wish I would know more about geology. We see the active turbulence, so this is like the best explanation we could come up with. But of course, I mean, I've shown you basically all the data that we're having, and the rest is just detective work and like
There's a lot
lucky
more to know.
guesses. Yeah, so there's other processes taking place there. Oh.
I have a quick question on when you were counting the events, the frequency. The majority of it seems to be on when the ice is melting versus when the ice is freezing, or it seems to be.
Yeah, I would say it's like too little data to really make a big point of that. But yeah.
And where did you get the data that's directly from the observation as well, or?
When I count the events?
Yeah.
Yeah, so the mooring with the ADCP, the current profiler, and the deep CTD, that was out for 3 years. And there I just like put a threshold value in. I think current surges lasting for a day faster than 0.3 meters per second with the offshore component and the drop in density. And then I counted. And yeah.
Right. And the mooring, that's not part of the expedition, right?
That's part of the Neighbors campaign.
That's right. Yeah.
Igor Polyakov, University of Alaska.
So I was curious, that means that he has a few more moorings, and whether you could actually then build up the database a little bit to have an understanding. I was just curious in the sense of when you were there was no sea ice, you said, or very little sea ice?
Sea ice, yeah.
And the question is whether it is the thinner ice that will promote more of this frequency, or whether it's the ice-free condition that might promote more of these, because it seems, there was still partly ice that seems to occur more often in the counting, but that would be interesting too.
That would be interesting to see. And I guess this would also be something where you could like maybe even better work with model results to see like when these current surges can be triggered the best. And you also can really track down the atmospheric pattern that are behind there. Because I was a bit sloppy here and said like wind conditions, but I guess atmospheric people would like slap me on the fingers for just saying wind conditions. That's probably something way more specific that could be related to these continental shelf waves passing by, which would be a next step.
Actually, maybe I would have a follow-on question. So in order to basically excite these boundary wave propagation that, for strong wind events, would that also imply that storms would have to be happening over a certain area in order to actually trigger those, as opposed to, because we like to think about, an increasingly ice-free Arctic, of course, has a local implication. If you have a storm locally, that will excite maybe internal waves locally, but then this type of mechanisms might also be excited, but not for every storm at every position.
That's an absolutely great question. I think one of the most important open questions related to this mechanism of mixing is, does it happen at this point, or does it happen like all around the rim of the Arctic? And that is tied to the forcing that comes to it. And something that we want to work on, if we find the time for that, is I was talking to Melinda Webster from University of Alaska, and she has a map of Arctic cyclones. And it seems that the occurrences of these current surges that we recorded in the mooring coincide with the presence of Arctic cyclones regionally in the Laptev Sea, which would be an indicator for like a more local distribution of these mixing events. Then again, regional cyclones somewhere else could do the same, but this is really tricky to answer, and that would be work for the future. Very interesting to look at.
Okay, any more questions? Oh, there's one more. Danke.
Yeah. Are there, kind of following up on that, are there remote sensing proxies for this process that you've been able to identify, or is
That's an amazing question. So we did, like, this mixing process did something to the surface layer. So it locally cooled the surface layer and made it a little bit more saline. This is something you can, in principle, detect with satellites. Now I have no idea about satellite data, but this was also on my list of things to look at, that because then you could really track down the temporal evolution, because you have, like, I guess, a couple of more pictures than just one in general. And also you could see what the spatial footprint of these events are. Are they like along the slope, or is it just like one little blob? And that would be really, really interesting. And also these satellites, I think they can detect like ocean color. And maybe you could also see like the fluorescence signal, the algae growth, and could like extrapolate from there like a magnitude of how much algae is excessively growing at this position. So that would be super interesting. And if anyone has ideas like how to really work with satellite data, I would love to talk to you, but I have no idea. So yeah.
Okay. Well, let's thank Kiki again for an excellent presentation.
Thank you.
And I should say, so Kiki is a local, so she has an office at she sits at the Oden Institute in the Peter O'Donnell building down on main campus. And yeah, please come and visit her, and if you're interested. Thank you.
Yeah.